Hello everyone, in this video I am going to explain double integrals with an example. How to use double integrals to find volume of a solid, some application of double integrals. So double integrals can be used to find volume of the solid. Suppose f of xy is a positive function over a rectangular region R in the xy plane. We may interpret the double integral of this function f over this region R as a volume of three-dimensional solid region over the xy plane bounded below by R and above by this surface that is equal to f of xy. So how to calculate volume? Formula is this: volume V is nothing but double integral over this region R, the given region R, of f of xy dA, this area element dA. This is dy dx or dx or dy. This can be dx dy or dy dx. Let's take up some examples to illustrate this. So in this example, we are going to calculate this double integral over the region R, where the function f of xy is 1 minus 6x square y and the region is a rectangular region here. X is varies from 0 to 2 and y varies from minus 1 to 1. So it is a rectangular region. So according to the discussion, this double integral over R f of xy dA, as I said, dA is nothing but dx dy or dy dx. We can interchange this order of integration. Here I have taken dx dy. Accordingly, we write the limits, corresponding limits here. So this is nothing but double integral. This is the function 1 minus 6x square y dx dy. So here first we integrate with respect to x, then with respect to y. For x, the limits are here given in the question. It is 0 to 2. So lower limit is 0, upper limit is 2. Then with respect to y, similarly y varies from minus 1 to 1. So the limits from minus 1 to 1. So first you need to integrate this with respect to x, keeping y constant. So integral of 1 with respect to x is x. Similarly, integral of 6x square y with respect to x. So 6y is constant. So 6y into integral of x square, that is x cube by 3. 3 ones are 3 twos are. So we can cancel to get 2x cube y. You have to put the limit 0 to 2. Then with respect to y as it is. Next, we have to apply the limits here. So limits for x here. Since we are integrating with respect to x first, so this limits is for x. So first put the limit x here, 2 upper limit 2 minus 0 lower limit minus 2y constant we are applying for x cube, this limit for x cube. So 2y taken outside, then put the limit for x cube. So 2 cube minus 0 cube, 2 cube is 8 minus 0. So what we get is 16y. Then with respect to y we have to integrate. So now we integrate with respect to y here. Integral of 2 dy, it is 2y minus 16 into integral of y, that is y square divided by 2 simplifies to 8y square. Then the limit minus 1, 1. Put the limit here for y, 2 into 1 minus of minus 1. So plus 1, 1 plus 1, 2, 2 into 2, 4 minus 8y square. So 1 square minus minus 1 square. So 1 minus 1 goes off 0. So we get 4. Since the double integral can be interpreted as a volume of the solid, so here I have written the units as cubic units. Since it actually gives the volume of this solid which is bounded above by this surface 1 minus 6x square y, z is equal to 1 minus 6x square y and below by this region, rectangular region. So the volume actually is 4 cubic units. So this is how we calculate this double integral over the given region R. Here the region was rectangular region. In general, the region, need not be a rectangular region, it is of any shape. So here we consider the next one. Next example, when the region is not a rectangular one. So here in this example, we are going to find the volume of the prism whose base is a triangle in the xy plane bounded by x-axis and the lines y is equal to x is equal to 1, and the top lies in the plane z is equal to f of xy, that is 3 minus x minus y. So this is the solid we are discussing about. Here in the figure A, we can see that solid, and to find the limits we need that region. In figure B, here we have the region, that is this region bounded by x-axis, lines y is equal to x is equal to 1. So here you can see this is the line y is equal to x, straight line passing through the origin. This is the line x is equal to 1 parallel to y axis, and the line x axis y is equal, that means y is equal to 0. So here this is the region of integration. So from this region we need to find the limits for integration. Suppose we want to integrate with respect to y first, then draw this line parallel to y axis in the region. Here we can see this line going to enter the region at some point and exit the region at some other point. These are the limits for y. See here, this is the line. So lower limit for y is this line in this region, the region bounded below by this line. So y is equal to 0. So lower limit for y is 0, and upper limit, here you can see this is bounded by above by this line, that is y is equal to x. So limits for y are y is equal to 0, y is equal to x. To find the limits for x, we look for minimum value of x and maximum value of x in this region. Clearly minimum value of x is 0 and maximum value in this region for x is 1. Or you can interchange the order of integration here. So if we want to integrate with respect to x first, then with respect to y, here you have to write the line parallel to x axis in the region, and we look for limits for x. Here we can see x is equal to y, x is equal to 1. So limits for y are y is equal to 0, y is equal to x. Here we are integrating with respect to y first, then with respect to x. So this is the double integral, required integral. Integrate with respect to y first. So it is 3y minus x is constant since we are integrating with respect to y. So xy, x into integral of 1 dy. So it is xy minus y, integral of y with respect to y square by 2, limit 0 to x. Put the limits for y and simplify, we get 3x minus 3x square by 2. Integrate this with respect to x, we get 3x square by 2 minus 3 by 2 into x cube by 3. 3 goes off, simplify and put the limit 0 to 1, simplifies to 1. So this is how we find or how we calculate volume of the given solid using double integral. So these are some examples to illustrate double integrals and application of double integrals. I hope you like the video. Thanks for watching.